Hey everyone, welcome to the fascinating world of radicals. Don't worry, we're not talking about extreme sports or anything like that. In math, a radical is just a fancy way of talking about roots like square roots and cube roots. You know, the stuff that asks, what number multiplied by itself gives me this number? The symbol we use for a radical is this cool-looking checkmark thing. The number under the radical sign is called the radicand. So, in 9, the radicand is 9. Easy peasy, right? Now, when we simplify a radical, we're trying to find its simplest possible form. It's like finding the neatest and tidiest way to write a number. This might sound a bit abstract now, but trust me, it'll all make sense soon. Let's dive in and explore how to simplify radicals, starting with those involving perfect squares and cubes. Before we tackle the tricky stuff, let's start with the basics. Simplifying radicals with perfect squares and cubes. This foundational knowledge will make the more complex problems much easier to handle. Remember perfect squares? They're the numbers we get by multiplying an integer by itself. These numbers form the basis of many mathematical concepts and are essential for simplifying radicals. For example, 4 is a perfect square because 2 times 2 equals 4. This simple multiplication is the key to understanding how perfect squares work. Similarly, 9, 3 times 3, 16, 4 times 4, and 25, 5 times 5, are all perfect squares. These numbers are easy to recognize and remember. Perfect cubes are similar, but instead of multiplying a number by itself twice, we do it 3 times. This concept extends the idea of perfect squares into 3 dimensions. So, 8 is a perfect cube because 2 times 2 times 2 equals 8. Understanding perfect cubes is just as important as understanding perfect squares. Other examples include 27, 3 times 3 times 3, and 64, 4 times 4 times 4. These numbers are fundamental in various mathematical applications. Now, simplifying radicals with perfect squares and cubes is super easy. Once you recognize these perfect numbers, the process becomes straightforward. Let's say we have the square root of 16. This is a common problem that can be quickly solved using our knowledge of perfect squares. We just ask ourselves, what number, multiplied by itself, equals 16? This question leads us directly to the solution. The answer is 4, so the square root of 16 equals 4. This method can be applied to any perfect square. Similarly, if we have the cube root of 27, written as the cube root of 27, we think, what number, multiplied by itself 3 times, equals 27? This approach simplifies the problem. The answer is 3, so the cube root of 27 equals 3. Recognizing these patterns makes solving cube roots much easier. See, simplifying radicals with perfect squares and cubes is a piece of cake. With practice, these problems become second nature. But what about when we encounter numbers that aren't so perfect? These situations require a different approach and a deeper understanding of radicals. Don't worry, we'll explore that in the next section. Stay tuned as we dive into more complex radical simplifications and learn new techniques to handle them with ease. Now, things get a little trickier when we deal with radicals that don't have perfect squares or cubes as radicands. These are the numbers that don't neatly fit into our usual understanding of square roots or cube roots, making them seem more complex at first glance, but don't fret, we can still simplify them. The process might seem daunting initially, but with a bit of practice and the right approach, it becomes much more manageable. The key is to find hidden perfect squares or cubes within the radicand. These hidden numbers are like secret friends waiting to be discovered, and once you find them, the simplification process becomes straightforward. Let's say we need to simplify the square root of 50. At first glance, 50 doesn't seem to have any perfect squares, but if we look closer, we can find a hidden friend. 50 isn't a perfect square, but it does have a perfect square hiding inside it, 25. This is a crucial step in the simplification process. We can rewrite 50 as 25 times 2. By breaking it down this way, we make the problem more approachable. Now here's a cool property of radicals. The square root of a times b equals the square root of a times the square root of b. This property is incredibly useful for simplifying complex radicals. Using this property, we can write the square root of 50 as the square root of 25 times 2 equals the square root of 25 times the square root of 2. This step-by-step approach helps in visualizing the simplification process. We know the square root of 25 equals 5, so our simplified radical is 5 times the square root of 2. This final step brings everything together, showing the power of finding hidden perfect squares. We can apply the same logic to cube roots. Just like with square roots, Finding hidden perfect cubes within the radicand can simplify the problem significantly. For example, to simplify the cube root of 54, we recognize that 27 is a perfect cube hiding within 54. This recognition is the first step in breaking down the problem. We can rewrite 54 as 27 times 2, so the cube root of 54 equals the cube root of 27 times 2 equals the cube root of 27 times the cube root of 2. This methodical approach makes the problem easier to handle. Since the cube root of 27 equals 3, the simplified form is 3 times the cube root of 2. This final simplification shows how powerful it is to find those hidden perfect cubes. The key is to factor the radicand and look for the largest perfect square or cube that divides it. This strategy can be applied to a wide range of problems, making it a versatile tool in your math toolkit. With a bit of practice, you'll become a pro at finding those hidden friends and simplifying any radical that comes your way. Remember, the more you practice, the more intuitive this process will become, and soon, you'll be able to tackle even the most complex radicals with confidence. Now let's add a little algebra to the mix. Algebra often introduces letters into our math problems, which can seem intimidating at first. But don't worry, these letters or variables are just placeholders for numbers we don't know yet. They follow the same rules as the numbers we've been working with. Don't worry, simplifying radicals with variables is not as scary as it sounds. In fact, once you get the hang of it, you'll see that it's quite similar to simplifying radicals with just numbers. The key is to understand the properties of exponents and how they interact with radicals. The rules are very similar to what we've already learned. When dealing with radicals, whether they contain numbers or variables, the process remains consistent. It's all about breaking down the expression into manageable parts. Let's start with an example, the square root of x to the 4th power. This might look complicated, but it's actually quite straightforward if we apply what we know about perfect squares. Just like with numbers, we want to find the largest perfect square that divides x to the 4th power. In this case, x to the 4th power is already a perfect square because it can be written as x squared squared. In this case, it's x squared because x squared squared equals x to the 4th power. This means that the square root of x to the 4th power is simply x squared. Therefore, the square root of x to the 4th power equals the square root of x squared squared equals x squared. This is a fundamental concept that will help us simplify more complex expressions. What about something like the square root of x to the 5th power? This is where things get a bit more interesting, but the process is still manageable. Well, x to the 5th power itself isn't a perfect square, but we can rewrite it as x to the 4th power times x. This allows us to separate the expression into parts we can work with. Using the property we learned earlier, the square root of x to the 5th power equals the square root of x to the 4th power times x equals the square root of x to the 4th power times the square root of x equals x squared times the square root of x. This step-by-step approach makes the problem much easier to handle. The same concept applies to cube roots and higher roots. Understanding how to break down these expressions is crucial for simplifying them effectively. For instance, to simplify the cube root of x to the 9th power, we recognize that x to the 9th power is a perfect cube because x cubed equals x to the 9th power. This recognition helps us simplify the expression quickly. So the cube root of x to the 9th power equals the cube root of x cubed equals x cubed. This method can be applied to any radical expression with variables. The key takeaway is that when simplifying radicals with variables, look for exponents that are multiples of the index, the small number outside the radical sign. This strategy simplifies the process significantly. If the exponent is not a multiple of the index, break it down into a product where one factor has an exponent divisible by the index. This approach ensures that you can simplify the expression step by step. Remember, practice makes perfect. The more you work with radicals containing variables, the more comfortable you'll become. Over time, these problems will start to feel like second nature. Keep practicing, and soon you'll find that these once daunting expressions are just another part of your mathematical toolkit.